Good morning. The last 8 lectures have basically set up the basic equations of electrostatics, and for the next few lectures we are going to apply these equations and get some useful results. Let us again see what we have already done. From Coulomb's law we had that the electric field is equal to 1 over 4 pi epsilon 0 volume integral over any volume, the charge density dV divided by that is, the electric field is proportional to the charge at any point and inversely proportional to the distance between the charge and the location where the electric field is measured, to the square of that distance. From this we obtained various results. One of the results we obtained was that integral E dot dl with a minus sign to any point r from some reference point which I am not going to specify is a function only of r, and we call that function the electrostatic potential phi. So, this electrostatic potential phi does not depend on how we went from the reference point to r, it only depended on where r is. And from this we also obtained that the electric field is minus the gradient of phi. Also from this equation we obtained that surface integral over any surface, closed surface, that is what this 0 means, of E dot ds is equal to the total enclosed charge divided by epsilon naught, and this implied in turn divergence of E is equal to rho over epsilon naught. So, E as a function of r, rho as a function of r. So, these two equations are the fundamental equations we work with. One says that there is something called electrostatic potential, and if you take its gradient you get the electric field. The second says if you take the divergence of the electric field you find the source of the field, namely the charge density divided by epsilon naught. If you combine these two equations, last class we saw it is essentially saying divergence of minus gradient phi is equal to rho over epsilon naught, which is rewritten as del squared phi equals minus rho over epsilon naught, and this is what we call Poisson's equation. So, if I have to give names, this is Coulomb's law, this is electrostatic potential, this is gradient, this is divergence, this is Gauss's law, and this is Poisson's equation. So, this is what we have reached as of the last class. It is not very much, almost all of it you already know. Now, what we would like to do is to apply all these equations and do something useful. So, for that, let me first start with the concept of energy in the field. Now, we already have met this concept before. If I have a charge q and I have another small charge little q, we already know that however I move this charge from a position r naught to a position r, the amount of work I do to take the charge from r naught to r, work done on charge, which is equal to minus integral q e dot dl from r naught to r, is a function only of r naught and r, and therefore, this came out to be q phi. So, we have already met work. Now, the question is, supposing instead of this problem I had a slightly different problem. Supposing I had a charge q and I wanted to bring another charge, say minus q, close to it. Now, obviously, I do not have to do any work. In fact, I have to do negative work to bring the charge there. But where does that work go? If I brought a plus charge here, I did work to bring that charge there. So, I did some work, but where does that work go? One thing I know is that if I now let this charge free to retrace the step that it took to come here, I do some work, if I release that charge, the forces of electrostatics will accelerate that charge. So, in the end I expect kinetic energy of charge would be equal to work done. That is, this work that I did to bring the charge up to here, if I let the charge free to move along this path, then the charge will speed up, and by the time it reaches out here, it would have gained enough kinetic energy exactly equal to the amount of work I had to do to push that charge up there. This is what I expect, and I expect this from analogy with gravitation. I know that if I have a mountain and I have a rock and I roll up that rock to some point, I did work on it. The amount of work I did on it was mgh. If I let that rock go, then the total kinetic energy of that rock, both the linear momentum and the rotational momentum, all of it put together, must be equal to exactly this mgh. That is, it rolls down the hill and converts gravitational potential energy to kinetic energy. This, by the same analogy, I expect that if the charge moves along that same path without me slowing it down, it will pick up kinetic energy like the rock exactly equal to the amount of work I had to do to push it up. The mgh we call as potential energy, and the work done here we call as electrostatic potential energy. So, it is the same concept. This is gravitational potential energy, this is electrostatic potential energy. Well, that is a nice idea, but now my question is, supposing I had a bunch of charges n charges. How much work do I have to do to put those n charges together? In other words, how much potential energy do the n charges represent? Now the answer is like this. Let us say I have charges Qi at positions Ri. So how will I do it? First I will take, let us say that this is very far away, infinity. I will bring Q1 to point R1. There are no charges anywhere in the universe. So there is no force, electric field is 0. So this Q1 comes through without any work done on it. So W1 is equal to 0. I did not have to do any work to bring charge 1 to the point R1. Let us now bring the next charge Q2 into this region. Q2 is brought to position R2 from infinity. But as Q2 is brought in, it must fight against the electric field exerted by Q1. So due to Q1 there is an electric field, and this electric field is present all along the path taken by Q2. So Q2 does work. How much work? Well, Q2 does work W2 equal to Q2 times the electric field due to Q1. So Q2 times Q1 over 4 pi epsilon naught 1 over magnitude R1 minus R2. This is Q2 times phi. Now I bring a third charge in, Q3 to position R3. Now Q3 must do work not only against the electric field of Q1, it must also do work against the electric field of Q2. So W3, which is the amount of work I had to do to bring Q3 in, would be equal to Q3 times the potential due to Q1, which is Q1 over 4 pi epsilon naught 1 over magnitude R1 minus R3 plus Q3 times the potential due to Q2. One over R2 minus R3, and so on and so forth till we bring in n charges. So how much work do we have to do overall? We have to do W1 plus W2 plus W3 plus etc. up to Wn. So the total work we have to do, we call it W, is equal to a sum I equals 1 to n of Wi, where Wi is each of these terms, which is sum I equals 1 to n of another sum j equals 1 to I minus 1 Qi Qj over 4 pi epsilon naught 1 over magnitude Ri minus Rj. Where did I get this? Take any particular I that corresponds to a particular Wi. That Wi contains Qi times a summation of terms. And what are those terms? They are Qj over 4 pi epsilon naught Rj minus Ri magnitude. Since its magnitude, it does not matter whether it is Rj minus Ri or Ri minus Rj. So, this represents the total amount of work I had to do to bring all the charges in, and you will notice it is not a very simple expression. We will need something to do some work to make sense of what it is equal to. It is not a very obvious expression, and we do not know how to calculate what it adds up to. But there is a simple way of understanding what this actually is, and let us see how that simple way is. Your textbook actually gives another way, and you should read both approaches and learn from both. The idea is as follows. Let us say I have some charge distribution rho of r, and I want to know how much energy is stored up in this charge distribution. This charge distribution could be in the form of n point charges, or it could be in the form of a charge cloud. Now, I am going to assume that this charge was built up bit by bit by bit. So, at t equals 0, no charge. At t equals say epsilon, or say t equals t naught, I have everywhere epsilon rho of r. That is, I have taken 1% of all the charge and put it everywhere. The shape is the correct shape, but much less charge, only 1% of the charge. At t equals 2 t naught, I have twice epsilon rho of r, and so on and so forth. At t equals say n t naught, I have full rho of r. So, slowly in time I am bringing charge in and building it up. At any given time, let us say t equals k t naught, the charge density that is present is rho of r times k epsilon. Okay, this epsilon is nothing but 1 over capital N. So, you have some fraction of rho of r, k over n of rho of r. So, what is the potential due to this rho? Well, we know the potential. Potential is 1 over 4 pi epsilon naught volume integral k over n rho of r prime over r minus r prime dV. This k over n is a constant, just pull it out. So, what do you get? K over n is a number times 1 over 4 pi epsilon naught volume integral now the quantity in square brackets is nothing but the final potential due to this final charge. That is the definition of potential. The definition of potential is, if I know all the charge, this is how much it is. So, it is equal to k over n phi of r. So, at t equals k t naught, phi is equal to k over n phi of r. And I am going to introduce a little bit of charge. How much? 1 over n rho of charge. So, how much work do I do? Well, in bringing in this small amount of charge, I am not changing the amount of charge present here by much. So, the potential is essentially constant as I bring in the charge. So, I can say the amount of work I do, delta W, is equal to rho of r over n times k over n phi of r. This is the amount of charge present times dV, the volume. So, this is the amount of charge which is being brought against this potential, but now I have to integrate over all space. The total work I do is the sum of all these W's. So, it is total W is equal to sum on all the delta W's. But if you look at this expression, it is a very simple expression, because it is a volume integral rho of r phi of r dV, that part is common, times 1 over n squared times sum on k equals 1 to n of k. K is the only varying part, everything else is constant. But we know what sum on 1 to n of k is. It is k into k minus 1 over 2. Approximately I am going to say that this piece is n squared over 2. The n squared cancels out, you are left with half. This is a very important result. Let me write it down. You can derive it in many ways. It is not the only way to derive it, but what it is saying is energy required to build up a charge distribution, and the charge distribution is rho of r, is equal to 1 over 2 volume integral rho of r times phi of r dV. Let me just sort of review, because I think it probably went too fast. I have a charge distribution here, okay? It can be anything. In order to calculate how much work I did, I bring in this charge distribution little by little, 1% at a time, 0.1% at a time. So, when I am bringing say the 50th percent of this charge distribution, I am going from 49% to 50%. So, the potential that is there is 49% of the final potential. That is what this k over n is telling me. Potential has the same shape because I have kept the shape constant, but the magnitude is less. Now, the amount of work I did, well, I am working against a weaker potential, but exactly the same shape. So, I do less work. How much less work? K over n of the work. What is the total work I do? Well, it is fairly obvious, I think. Initially, I do no work at all. Finally, I do full work. Halfway down at 50%, I do half work. So, really the work I do is a triangle. The delta W versus say time goes like a triangle. Initially, I did not do any work, because to introduce the first percent of charge did not take any work at all. There was no field to begin with, so there was no work done. Finally, when I introduce the last percentage of charge, I do a lot of work, because I have to introduce it against the full potential. So, it is a triangle that I have, and each time I am introducing a bit of charge, I am doing this much work, and the total work I do is the area of this triangle. And you know that the area of a triangle is the base into height divided by 2. That is where this half comes from. because rho into phi integrated over all space is like assuming that from the beginning to the end I was working against this potential. Supposing to introduce the first charge and to introduce the last charge, I had to work against this potential, then the amount of work I would have had to do is the full area of the rectangle. But I know that actual work I did was only 1/2 of that rectangle. Initially I had to do very little work, finally I had to do lots of work. So that is where the half comes from. It is a very important factor of 2. It will keep coming back in all kinds of places. So you should feel comfortable when you see 1/2 integral rho phi dV. So that is the energy that is required to build up any charge distribution. So what that means is, if I have 4 charges in a square, and they are on separated by distances of a, it is fairly easy to calculate the potential, because you know the distances. This distance is a root 2. So you can calculate potential of any of these charges. So the potential at all the charges is equal, and that phi naught is equal to q over 4 pi epsilon naught times, for this potential, the potential due to the second charge is 1 over a, the potential due to the third charge is 1 over a root 2, the potential due to the fourth charge is again 1 over a. So this is the potential. How much is the stored energy? Well, it is q times phi naught. This is the stored energy here, plus q times phi naught plus q phi times phi naught 4 times, divided by 2. The factor of 2 comes from the fact that when I brought the first charge, I did not do anything. When I brought the second charge, I had to do something. It is only when I had brought the last charge that I did the full amount of work. Okay. Now, the whole purpose of calculating work in getting a collection of charges together is because it has a lot of importance to electrical engineering. And you all know what element that is. That is the element we call the capacitor. You have already seen it in many places. Supposing you have 2 plates, and the plates are separated by a distance d. The plates have an area A. I am sure you have seen the formula. The formula saying C is equal to epsilon naught A over d. Now, what exactly is this expression saying? What this expression is saying is, if I take the top plate and add a charge q to the top plate, and if I look at how much work was done to introduce that charge q, I can work out how much stored energy there is, and the stored energy that is present there is in the form of positive charges sitting on the plate due to this charge q associated with a potential, a voltage on that plate. So you have seen the formula Q equals C times V, and you have seen the formula that energy equals 1/2 CV squared, or is equal to 1/2 Q times V. Now, if you look at this formula, you can see that it's essentially the same thing. This is nothing but Q, this is nothing but V, and you have your 1/2. So, the formula of a capacitor is really saying the same thing as energy in an electrostatic field. And what we are going to do for the next lecture or so is we are going to look at the capacitor, but we are not going to look at it as a circuit element, we are going to look at it as a storage, energy storage due to a electric field. I have one preliminary that I have to complete, so let us get that out of the way. Last time I had told you that if you have a metallic body a conductor, then inside the conductor electric field is equal to 0 identically. I did it by two different arguments. One argument said I can't have circulating currents, and the other argument said I can't have radial currents. The argument against circulating currents was that if I have R1 to R2 of E dot dl, and I call this R1, I call that R2. If I go this way, I would be going with the electric field. If I went this way, I would be going against the electric field. And so, the results would be different unless this was identically 0. That was for fields that were going round and round. What about fields that were going away from a point? Well, if you have any such region, look at it from above. What you have is an electric field that is pointing outwards. That electric field is steady, which means we can use Gauss's law and say there is a charge inside. However, that electric field also represents a current. So, this electric field is also equal to the current divided by conductivity sigma. So, on the one hand you had surface integral E dot ds equals q enclosed over epsilon naught equals constant, because we are talking about equilibrium. On the other hand, you had that this thing is also equal to surface integral j dot ds with a 1 over sigma, which meant that charge was continuously going out of this cylinder. But if charge is continuously going out of the cylinder, it is actually equal to minus 1 over epsilon naught dq dt. The amount of charge that is inside must be reducing if charge is going out. This says charge is constant, this says charge is reducing. You can't have both. The only way to make sense of having two separate statements like this is to say that electric field is equal to J is equal to 0. So, that is what it says. The electric field is 0 inside a body. Now, if that is so, then there is an obvious conclusion. The conclusion is, if I have any metallic body and I take any 2 points r1, r2, and I draw a line connecting r1 and r2 that is entirely inside the body. It does not leave, it stays inside the material. Inside the material, electric field is 0. What does that mean? It means integral r2 to r1 E dot dl, and let me put a minus sign there, is equal to phi of r1 minus phi of r2. So, this E dot dl integral is nothing but the potential difference between r1 and r2. Electric field is identically 0, left hand side is 0. Therefore, phi of r1 minus phi of r2 is equal to 0. So, it means that every point inside or on the surface of a conductor is at constant potential. Any 2 points have the same potential. So, this is why we are able to give voltages to conductors, and this is why when we come to a capacitor, we are able to talk about voltage of a plate. We are able to talk about voltage of a plate because if I take a point here and I take a point there, I can draw a line connecting those 2 points which lies entirely within the plate. The electric field is 0 and therefore, the potentials are the same. Therefore, we are able to say that every point on the plate is at same potential. So, instead of talking about phi of r, so there is a, it is a function of position, we simply give the voltage. We do not say that this is the voltage of the plate at this point, whereas that is the voltage of the plate at that point. At all points on the plate, voltage is the same. Okay. Now, at the end of last class, I had derived Poisson's equation. Let me write it down again. It says del squared phi is equal to minus rho over epsilon naught. Now, what does this say for a one dimensional problem? It says, supposing phi and rho are functions of x only, let, okay. Then I can write this equation down. It says d squared phi dx squared, where phi is a function of x, is equal to minus rho of x over epsilon naught. All right. Now, this equation happens to be very important. It is important because supposing I have a capacitor system, I have a plate and another plate, and let us suppose that this direction is x. I choose to ground one plate and the other plate I put at voltage V naught. All right. And I want to know how to solve for rho and how to solve for phi. So, I have to solve this differential equation, but I have two pieces of information. Phi of 0 is equal to 0, phi of this distance is given as d, phi of d is equal to V naught. It's a differential equation, second order ordinary linear differential equation, very simple equation to solve. But there is something that makes it simpler still. The region between the plates is air, which means there is no charge there. So, I also have for 0 less than x less than d, d squared phi dx squared is equal to 0. Now, we know all about solving this particular differential equation, and we know that the answer is phi is equal to a plus bx. Just integrate this with respect to x, and the integrating constants will give you a plus bx. So, if you now substitute a plus bx and try to solve the boundary conditions, you will have a plus b times 0. So, a is equal to 0, and on the other side a plus b times d is equal to V naught. The first equation allows us to get rid of a is 0. So, there is no a here either. The second equation allows us to get b. So, that implies b is equal to V naught divided by d. So, I can give the final answer. I can say that the potential phi is equal to V naught over d times x, 0 less than x less than d. At x equals 0, phi is 0. At x equals d, phi is V naught. So, it satisfies the boundary conditions. So, from this I can find out electric field. The electric field is minus of the gradient of phi, but here only one direction matters. So, it is minus d phi dx. So, it becomes equal to minus of V naught over d. So, if I have a second plate at voltage V naught, first plate grounded, the electric field is in this direction. It is negative. It is negative because for a positive voltage here, positive charge will come here, negative charge will come here, and so the electric field is towards the first plate. Now, this still does not tell us what we really want to know. It still does not tell us what is rho, all right. What is the charge on the plates? Well, for that we go back to some more high school physics. We apply Gauss's theorem. Now, let us look at it. For example, let us look at plate at x equals d. Now, we have from here that the electric field is a constant and is pointing towards the first plate. So, if I have such a situation, what I can do is I can say I will take a surface that looks like this. This surface has a flat region with an area dA. It has a sloping region with a length, call it h. So, the flat area is dA, sloping area is 2 pi r, where this is r, times h, and dA is going to be equal to pi r squared. Now, the electric field is coming straight out, which means it is tangential to the sloping area. So, I am only going to see the contribution of the electric field on the flat surface. What is more, inside the material I know that electric field is 0 everywhere. So, this piece does not give me any contribution. So, if I do surface integral E dot ds, I only get one surface contributing, that is 2 pi r times pi r squared times this electric field, that is minus V naught over d. However, this normal to the surface is pointing in the negative x direction. So, this minus sign becomes a plus sign. So, this gives me the area times the electric field must be equal to the charge divided by epsilon naught. Well, what is the charge? Charge is nothing but the amount of charge on the plate times the area of that region. So, pi r squared over epsilon naught. So, I can cancel out pi r squareds and I get an answer which is very familiar, which is that the electric field, what I call the E normal, which in this case is V naught over d, is equal to the surface charge divided by epsilon naught. I have skipped a point here, and so let me cover that before I complete this problem. When I talked about a metallic body, I said the electric field is identically 0. If the electric field is identically 0, then the question comes, where is the charge? Okay. Well, you know the construction. I take an imaginary surface that lies entirely inside but near the surface of the body. So, at every point on that imaginary surface, electric field is 0, which means surface integral E dot ds is 0, which means Q enclosed equals 0. So, there is no charge enclosed inside a metallic body, yet a metallic body can carry charge. It can carry charge because we can always take an isolated metallic body and put charge on it. So, where is the charge? The charge must be lying on the surface. The charge arranges itself on the surface in such a way that interior of the metallic object has no electric field. So, now going back to this problem, I have a normal electric field, I have no electric field in there inside the material, I have some surface charge. I have to relate the normal electric field to the surface charge. So, what did I do? The area times the normal electric field is equal to the charge density times the area divided by epsilon naught. So, this allows me to connect the normal electric field to the charge density. So, what do I get? I get rho naught is equal to epsilon naught V naught over d. Now, the charge on the plate is this charge density multiplied by the area of the plate. So, Q is equal to area times rho naught, which is equal to epsilon naught A over d times V naught. And this is where we come to our standard result, which is Q is equal to CV. This quantity C, which we call capacitance, is the thing that we are used to. This is what we see in circuit theory. However, in electric fields, when you study it in electrostatics, it is a more general thing, because it is entirely possible that I create, say, a sphere I ground the bottom, I hold one part of it at V naught, I hold another part of it at minus V naught, and I ask how much energy is stored. It does not fit into this simple form. This simple form is only good for two plates. What happens if I have multiple plates? We will see in a short while, maybe in the next lecture or two, that no matter how many plates you have, you can generalize this concept of capacitance and define a matrix, which matrix equation which basically says the same statement. Okay, let us take one more example to understand these concepts. Supposing we have a spherical region filled with charge, and you are told that the charge is a function of radius only. It does not depend on theta, it does not depend on psi, it is radial. And you are told that the electric field inside this material is constant. Once it leaves the surface, of course, it is not constant, but inside the electric field ER is a constant. So, the problem is to find out how much charge there is, what is the kind of charge there is, and to find out the capacitance of an equivalent metallic sphere containing the same charge. Problem is straightforward. All we have to do is apply divergence theorem. If I take an imaginary sphere of radius r, let us assume the sphere itself is radius a, then I know that surface integral E dot ds, which is equal to E r times 4 pi r squared. This is the surface area, this is radial electric field, is equal to charge enclosed divided by epsilon naught. What is the charge enclosed? It is nothing but integral rho of r dr times 4 pi r, I put r prime, divided by epsilon naught. notice here that I have put Q enclosed. So, what it means is the electric field here depends on the charge that is inside the sphere, it does not depend on the charge that is outside. We worked this out. We found that if you took any region and you put a charge outside, the charges field lines do not contribute to E dot ds. So, you can now have that the electric field is related to charge density. Now, this is an unwieldy problem to look at, but luckily we can go to the differential form of this, which is divergence of E is equal to rho over epsilon naught. Usually you would prefer to work in this because of the symmetry, but since I am giving you the electric field and I want to calculate rho, it is easier to work with the differential equation. For spherical coordinates, this is what the equation becomes, and all you have to do is to differentiate, because E r is nothing but a constant E naught. So, substituting in, we can easily obtain rho. I will complete the problem next time, but I want you to try it out yourself, because most of the ideas that we have talked about in electrostatics can be tested out by solving problems like this. For example, look at what happens if you choose a Gaussian cylinder that is larger than A, and try and plot out the electric field and potential as a function of r.